Any questions from last class? Okay, so let's continue. Last time we had a little bit of confusion about the transformation. So I'll clarify that before we continue. And today, at least we will finish up one complete cycle of reasoning. Why quantum field may need to be introduced, as we have been thinking about, and we'll eventually determine the exact form of a scalar field in this case. And in particular, the main focus must be how different elements of special relativity and quantum mechanics works out together, right? So the whole point of this exercise is for you to understand there's actual tension, right? When you try to smash them together, and they don't want to just meet each other easily. So the whole point is to understand how tight the tension is and how they eventually manage to combine together in such a way that there's almost uniform quantum field. And so I would to elaborate some of those, like what is the real tension between causality and quantum mechanics. So eventually that's the part that you want to understand. So this is more of, I would say, quantum field theory has several aspects. And a lot of times, intro quantum field theory class is full of those calculational aspects. Whether you can just compute the gamma matrix traces, and you can use that to compute the S matrix and amplitude, when you can compute the scattering and so on and so forth. A lot of that which is necessary, right? Because if you are limited by the calculation ability, you cannot go through the physics, right? It's just overwhelmed by the calculation. And you just lose the chance to actually look at the physics side. So it is extremely important that you are equipped with a calculation ability. So when you study QFT, therefore you have to spend time to teach your hand and actually learn the technical aspect. But then in this course, I decided to instead go through first the conceptual part of the story, which is very important and oftentimes miss out a lot of courses on QFT. So hopefully you get that. But after that, we will start going over slightly more, standard course of QFT learning course. Okay, we're gonna start talking about scalar field theory, classical field theories, and then equations of motion, and so on. And so we're gonna go through that. But hopefully you appreciate the exercise that we are doing. All right, so let's go through that quickly. And we say we're gonna construct a scalar field, and then the first property that I wrote down, we consider to satisfy is that this should vanish outside of icons of causality. To refocus, first of all, our mission or real scalar field. Okay, and because we are interested primarily causality restriction imposed on observation. Remember that, right? If there are two observations which are causally disconnected, they should not affect each other. So that is captured by this. So observation is associated with the permission operators. So that's why we pick that up. And then two properties which are associated with did I say this? Oh, that's fine. Translation, was that sign right? Minus sign there? Ah, yes. Okay, good, thanks. Or and then finally, we made a simplifying assumption to say that this is a linear combination of what I call a base hat or X, alpha B, G. So there was a little bit of confusion about your sign versus the exercise ID. Okay, so let me just sort it out real quick and then move on. There are two things, right? In quantum mechanics, there is state and then operator. So for instance, we have a state, and there can be a quantum operator. Like that, we can ask the expectation value of that operator, right? On that, with respect to that state living in the hyperspace. Now they transform oppositely, right? The first is okay. Here's one measurement, but then let me also do the measurement in terms of state, which is transformed with respect to that thing, and then we can ask the same question. Okay, can I do the measurements? Yes, you can. You should be able to do it, right? You just rotate the apparatus, you can measure the same thing, for instance. So in terms of original state, obviously this is written as a U O operator. So I mean, the point of this little quick expression, as you all know, is that if state transform according to this, so shredding the picture, but then you can say the same thing, that the state doesn't change at all, but the operator has been transforming like that, right? So we talked about the fact that if I have now a state in the Fock space T, obviously I can ask about Lorentz transformations. So this is how state transform in the hyperspace. So now you can look at this operator, obviously it is consistent with what I just said, right? It is transforming according to the rule that I have to use. So here is the shredding picture, here is the Heisenberg picture. Same thing. So we talked about the same thing. Can I do the transformation of T to the I E dot A? Acting on that. That was how a state transformed in the hyperspace. And obviously the operator should transform this according to that. And they opposite because if there is a say axis, which is one thing, there's an object which is another thing. Just like we had a state and operator. There's a state frame. And then there's an object. If you want to move the object actively, called active transformation, that can be achieved by moving the coordinate system backwards, right? So they transform in an opposite way. So active transformation or passive transformation. Okay, that's exactly what's happening here. So once you sort this out, then you should be able to check that all the equations. Okay, let's move on. Question. All right. Yes.
Why the pattern G has what's constant?
You mean this one? Yeah. So okay, let me wrap it up. The last discussion, and then let's which include that part of the discussion, and then let's move on. So first we said let's start with the 5, which was the assumption that I want to consider minimal construction first, right? So then we can construct all the observable out of that. So let's apply the 3 and 4. So first of all, we say let's consider 4 after applying 3. Say, this may take the form that now it's key because I remove the x and then alpha and then g of p alpha a. Now the part that now Lorentz transformation property, which says that I should be able to talk about this either that way or the other way around. This shouldn't matter because it's the same thing. Because I can just move on this side, right? So I can either use this form or I can move on this side, which is without a dagger, here dagger, which is fine. So then we learn from this exercise that F must satisfy property, and likewise G has to satisfy this. So if you use this version versus the other version, the only difference is whether you have to put your lambda versus lambda inverse. Okay, but in either way, that tells you that this f as a function should be Lorentz scalar function of a single Lorentz vector p mu. Right? Because this guy only has the p dependence in it. Therefore, f and g are Lorentz invariant function of again a single Lorentz vector p mu. So if you're given a Lorentz vector, you know how to construct a Lorentz invariant. Right? In this case, since I have only one guy, there's only one Lorentz invariant, p squared. Obviously, if I'm given several of p1, p2, whatever, if these were the function of several momenta, then obviously I have more than one Lorentz invariant, like this, that, and so on. But in this case, since I'm given on a single momenta, this is the only option, which is now completely independent of momentum difference, right? So it's the constant. That's why we concluded F and G are just constant, meaning just constant. Okay. So that was from the Lorentz theorem. Let's continue. So now let's consider the 1 and 2, the causality and hermeticity. So now we can write down. Did I think I did this part too, right? Last time. So reading that suggests that phi should take the form that it is this, and then let me write minus I p dot x plus alpha v whatever plus with p 0 is equal to p, or equivalently p squared is equal to, meaning on Shelby cross. That's all I'm saying.
Therefore, the F and G.
Yeah, forgot that. Very much. Yeah. Good. Now constant. Okay, so I'm gonna write this as f times, which is constant, which I can pull out of the integration, and then the first piece, which I'm gonna call it phi plus of x, and g by minus of x. To maximally confuse. The terrible is I just put minus plus and plus minus, and then it looks like a plus or minus. Yeah, maximally confused. Right. This is how you do physics, right? You just phrase things so that nobody can follow it or understand. Anyway, this is not my fault. This is neither Coleman's fault either. This is designed by Pauli and Heidegger. Okay, so authors of quantum mechanics, therefore you cannot complain. You should not complain. You don't have a right to complain. You just swallow. Okay, my heart. Minus means minus plus. You have to just whatever to. But let me explain physics by this. I'm not sure it is phrased in this way in any literature. I just thought about it. So here's my version. So you go, you think about yourself, you disagree, come back to me and let me know. Okay? For anything I say here during this class. Let's why they call this? So that plus here means that the positive energy or frequency mode. And this negative minus sign here means that this corresponds to negative frequency or energy mode. That's why we put that sign. What does that even mean, right? So let's understand it real quick. So therefore, phi plus now with absolutely clear sense come to the minus IP dot x, right? And then this thing is plus IP dot x. So this is negative frequency mode. If you just vary it very carefully, right? Okay, so let's understand that. I know you're not supposed to get it. Understand? Explain. So there is what I'm trying to say now is that I feel that this is a misleading nomenclature, which is a relic of history of the development of the quantum field theory. So let me explain what I mean by that. So suppose we have a wave function of usual quantum mechanics sense. Okay, so suppose we had a wave function in a usual quantum mechanics sense. Don't be confused with this operator that I'm trying to construct. Wave function. So if you are given a wave function which looks like either minus plus IP dot x. So in order to understand the physics meaning of that, you just plug into the Schrödinger equation, right? So I know how to solve this problem like that. Very good. And then you also know that this takes the representation of I times h bar times derivative with respect to the t. Okay? And remember this p dot x obviously has p0 t minus p vector x. So forget about the p dot x part, the vector part. So this shows you that if you just actually do it, you should get for minus sign, there's I, that gives another minus sign plus. And with the plus minus sign minus p0 sine of x. Right? So therefore now if you compare this thing with that, provided you're looking at the branch where p dot is positive, you know that the this sign corresponds to positive frequency wave function, and that part corresponds to negative frequency wave function. Does that make sense now? Okay. Not or yes? Hold on. Did that make sense or not? No?
Makes sense.
Okay. What I just did was I imagined that there's a wave function that looks like this. And then I just checked the Schrodinger equation to get interpretation of the meaning of the sign. And that sign meant that with the minus sign right there, that gives me energy by matching these two, which is equal to plus the P naught. So if P naught is positive, so I'm looking at the positive branch in the Lorentz space, that corresponds to positive energy wave function. With the plus sign right there, that corresponds to negative energy wave function. Okay? So if these were wave function of quantum mechanics, yes, you have every right to call it either positive or negative frequency mode. Now, what I'm gonna demonstrate in the rest of the lecture is that, yes, you can use that name, but every single one of those bits actually will be healthy positive energy mode. Will be. Okay? So I'm just telling you two things. One, there was that name, that's why this terrible choice of notation was picked by this guy, because they were thinking of that thing. They were thinking of constructing wave function rather than the quantum field operator. Okay? But we will see that there's a little bit of mismatch. Okay? So get the name of it, understand where they come from, but you have to sort it out physically, mathematically, what will be the correct interpretation of these signs, which we will learn today. Okay? So I just told you two different sides. All right, question.
Yeah, but you have also said the energy must be positive definite.
Yeah, so
But so and P0 must be bigger than 0.
Yeah.
And but that sometimes that will mean that there's some interaction.
So, sorry, contradiction is that.
So if energy was positive,
Yeah.
and if I pick the minus at there,
Yeah.
if I pick the plus at there,
Yeah.
then you have minus P0 right there.
Right. So good. So I was first focusing on the energy or P naught versus electric side, and then here is the timeline section. I'm looking at this branch, which is disconnected from that branch. So I'm just looking at this side. Then I'm saying this has the interpretation of a Planck wave carrying either positive energy or negative energy. You might say, what's wrong with that? I can have a little bit of negative energy. The point is, everything should be, energy must be bounded from below. Otherwise, I told you last time that there's a spontaneous population of particles, everything is unstable. So if this were part of the mode with the bound behind, yeah, it might be okay. But this is a pure Planck wave physics, and it only carries negative energy, nothing else. So that is completely this unstable physics to have. That's the sense people will panic. Like those guys will panic. Oh, shoot. We should walk away from that. Another question. Yes.
I think that this is based on the metric that time is positive and space is negative.
Good. Okay.
And is this a combination for the quantum field theory?
Yeah. So good. So there is that part of the thing. Meaning, he said that there's a choice of a metric. Whether I start with the +1 for temporal component and the -1 for the spatial component, you can pick the other way around. But I'm saying if you pick one choice once and for all, you have a unique interpretation. So if you flip the metric, then this becomes positive, this becomes negative. The point is that one is a state, the other is good. That nature will not change. Good. Another question. Yes. Sure. Yeah. Go ahead.
그 저기 3번씩 여기 옆에서 이제 하이엑스를 따라갈 때 그 알파 P 좌우로 붙어야 되는 거 아닐까요? 이제
Oh, I already worked that out. That's fine. Good. Yeah, you're right. So first I have to do this. Oh, yes. First you have to do it. So you have to write down this equation for this is 0.
Yeah.
Then you work it out, and then I use the fact that alpha P satisfies a particular property, like E dot Ts, E to the minus E dot S. This is equal to E to the minus I E dot X alpha P and so on. We derived these sort of equations before. So starting with that equation, acting on alpha from both sides, and then I use the fact to write as this. This is number, not an operator.
Okay.
Good. Another question. Very good. Good. Let's move on. Oh, I did not work that out last time, or just in case. If not, I will have to. You did. Good. Okay, let's move on. So where am I? Yeah. So good. So here is the answer. So now let's look at the causality part. Okay. So causality, which is 1. Although I can impose. Okay. Anyway, let me look at the causality first. Now, to this end, you recall that in addition to this part of the information, 5 plus is only a function of alpha, but not alpha dagger. 5 minus is only a function of alpha p dagger, right? Good. So then we already studied when we talked about the plot space. Alpha commutes with alpha, and then alpha dagger commutes with alpha. Are you okay with this slide notation? Yes. Good. So, on the other hand, thanks. So alpha p, alpha q, dagger. On the other hand, here I'm going to be careful. Right? Remember that, right? Good. So this is a simple harmonic oscillator attached to every single momentum mode. But this is a normalization factor to make it learn there, blah blah. We talked about that. Good. So now this already immediately tells me if I look at commutator, by the way, this is equal time commutation. So these are all equal. I'm really tempting. Time commutation. Is that okay? Or do you want me to write? Equal time commutator. Done? Okay, I don't have to write. Yes? Very good. Because what am I talking about? That was Hilbert space, right? Box space, Hilbert space. Hilbert space is defined on time slice. So everybody lives on that time slice. Same time zone. Okay? Therefore, whatever operator equation I wrote down back then, it was equal time commutator. Yes, good. So let's look at this. Therefore, the first line is that if I look at any correlation function with x, with y, this should be 0 so long as x, y are on space like separated or space like separation, which I will discuss why this is the same as this, because that is equal time commutator and this is space like separation. Are they always equivalent? Which I will explain momentarily. And second claim is if you look at this part, then will also be automatically true because of the fact that phi plus is always linearly proportional to alpha, phi dagger is always linearly proportional to alpha dagger. So if I naively say that this is defined on equal time slice, then you're happy, yeah? Because if this is equal time thing, then this is alpha, yeah, 0, obviously, good. This is alpha dagger is 0, good. But then the only thing that I need to explain is why, considering arbitrary space like separation is also the same as equal time commutator. Right? That's the only thing I need to explain. Or am I owe you more than that, or just that? That's that, right? Yes. Good. Am I doing that? Am I okay? Good. So let me explain that. So hopefully now I can just erase this. All right. So that is based on a simple observation, which is useful, powerful. So you want to know, and then once and for all, you want to remember. So this is time, this is x. This is light on. This is light on. Now I'm going to explain once clearly, slowly. And that should be yours from now, okay? So get the point. So let's look at a vector such that x squared is equal to some k squared. So if you're confused by this condition, consider that is the same as asking about this question. Okay, any Lorentz vector. Now let's consider a case where x squared, which is again k squared, is positive, which is time one. Okay, On the other hand, that is the same as x0 squared minus x vector squared. Which is equal to, again, some positive quantity squared. And this is hyperboloid. And then x0, the temporal component, will cross at plus minus k. Right? The solution to that equation, this is minus, this is plus. So only imaginary part, but this guy have a real solution where x naught is equal to k, for instance. Right? So time-like surface therefore is defined by hyperboloid, and it looks like this. It means that either plus k, or more precisely, plus square root of k squared, which is the same, this is going to get a positive, and then this negative hyperboloid, negative branch. So this is minus of, right? So this is a time-like vector. Now, what Lorentz transformation does for you is that given x mu, obviously it will transform like lambda times x mu. So it will move around. But the Lorentz inverse suggests that whatever you do, you stay in this hyperboloid. Good? So Lorentz invariance can move around this hyperboloid, but you never get out of that. If we consider proper orthochronal transformation, which does not flip the temporal side. Remember that. So proper determinant 1 orthochronous means that the temporal side is positive. So you just start here or there separately, but you never go from here to there, for instance. Good. That's what happened to the timeline. Let's ask about the space line. Because a lot of questions we ask here is about the space line separation. So is color blue fine from people in the back? Yes. Okay. So now if we ask, what about if this is minus k squared, which is negative? So we are asking the question about the space. And by the same reasoning, we immediately see that this is the spatial part cuts, meaning it has a real crossing at plus minus square root of k. The temporal part doesn't, right? So if I draw that thing, then it will look like this, which is meaning as either plus of yes, a square and a square, but not the same k here. There. Okay? So this is Lorentz invariant hyperboloid shifts defined by this equation. Again, what Lorentz transformation does for you is you move around on this thing, but with a fixed this equation, right? That's what Lorentz transformation does for you. But here you notice the one very important difference, which we will use immediately. So if you have a vector x here, but then in this case, there exists the Lorentz transformation x goes to lambda x in such a way that you can literally flip sending x to the minus x. Because that's on the same hyperboloid shift. So for space-like separated point, x vector can always turn into the minus x point. But time-like one, you can never do that. You got it? Good. Now we're going to make use of it immediately. Let's do it.
Professor,
Yes.
but the focal orthochronous will never flips the P0.
P0, but you can have yes, sorry. You can never flip it to P0 in a sense. Well, here I said that roughly, but yes, and you continue. Let me just know.
Yeah, but I think never mind.
Because it is not you have to make use of a spatial rotation too. So for instance, if you have this, you can always know that you can go here by spatial rotation.
Yeah, I got it.
Yeah. Good. Yeah. Okay. So with that, let's come back to here. Now you should see that any space-like separated vector can be put as just equal time slicing. Right? You can just move here. Boom, done. Right? So therefore, whenever I see space-like separated equation, that is saying that equal time commutator. Therefore, when I look at this equation, I can just use equal time commutator all there. Because I can just go to that. Good? That's Lorentz invariant operation. Moving on. we haven't, there is still one equation we have there. What about that equation? So causality demands that every single thing should commute, right? Because basically here, what I'm trying to say overall is that given Hermitian operator field phi, basically I'm asking overall, phi of x, phi of I, but is that zero outside of Lycon to be causal? And you see that this is decomposed into these three questions. Right, there's a plus part, minus part, plus part, minus part. If you look at it, it's decomposed into these three questions. Okay, so let's look at that. So therefore, let's look at this equation carefully. So let me rewrite this equation, which is equal to f times plus of x, g times minus of x, f times plus of y, g times minus of y. So that's the question I'm asking. And then I already answered this, that. So let me just write it across the line. That tells me fg and then plus of x, that's y, that's the first sort of term. And there's another one. There's another one, which is g of f, which is the same as f of g, because there are those numbers. That's all right. So in order to answer whether this field construction is completely consistent with the causality, I need to show when this can be done. Okay, let's do the exercise. So what is this guy? So first of all, I'm just gonna call this guy is equal to well, let me just evaluate, because that is this thing, and then that is the other one. So I can just evaluate this thing. There's double integral, because phi plus has that integration, and then phi minus has its own integration. So let me just write that as Q integration. Good. And then phi plus comes with e to the minus IPX, so that gives me e to the minus IP dot x. And then phi minus, which is this part, comes with e to the plus I momenta, which is set to Q, and then 1. And then this is proportional to alpha of P. Second one is proportional to alpha dagger of Q. So that is the thing that I need to compute. Okay, I just literally written down the definition of each of these expressions. That's all I need. Okay, so we know this commutator, which I already have written down here. So if I use that, there's a 2 pi to the cube, which kills that 1 over 2 pi to the cube, 2 times EP, that kills that. So the delta function that you should get. So this is what you should get. Okay, I'll take a moment. See if you can convince yourself. All right. So is this zero? Well, that's basically the question. Right? So therefore, so let me define this object as is done as a delta sub plus, because that's plus minus, and then x minus y, because that's Lorentz-Invariant function of x minus y, and then extra information, which I'm gonna put math square, because the EP has math information in it. So this is the function, Lorentz-Invariant function of x minus y and then m squared. Good. So now, what about this object? So let's just write down that thing. Therefore, we have the following equations: f g. So that's the same thing. Delta plus x minus y of m squared. And this is minus of the other way around, right? This is just minus that thing, but that was the definition of that thing. So that means this one. y minus x f squared. Okay, good. Now, again, the question was, is this zero outside of life? It is, otherwise, you're dead, and you should be able to see immediately. So this is actually O. This is actually equal to 5 plus x minus y and square if x minus y, so x that means is basically that range. Meaning the same as the first term. How do you see that? This is again Lorentz invariant function of x minus y, right? If you look at this expression, this is the manifest Lorentz invariant. Well, now manifesting, because you are educated. Before, what the hell? But now you know, right? This is Lorentz invariant, this is Lorentz invariant, everything is Lorentz invariant. Okay? And I told you that if you have a Lorentz invariant object, then obviously space vector operation is the same as x to the minus x. So if this is a function of a quantity argument something, it is the same as minus that being on space vector operation. Therefore, it is zero. Good. The causality is restored. Causality is incorporated well. In addition to that, which will turn out to be extremely important later, is that the second property, hermiticity, that this actually demand that if you look at this, right? If you take the Hermitian conjugate, this is real. This flips to the alpha dagger. This becomes plus. So you flip this around and then F star, G star, right? You just flip with the G star, F star. So in order for this property to be satisfied, you see that F star is equal to G. So therefore, this actually turns into modules. So now let's look at this equation and what does that even mean? So this guy is an operator which can, if acting on the vacuum, can create a particle, as we talked about, right? Or annihilate a particle, right? So you can take this operator and create a quantum state in a box space. But we know that the quantum state in quantum mechanics is defined as a ray, and it's defined only up to phase. Right? If you have a psi, if you multiply by the phase, that's the same physical thing. So therefore, we can demand that this is equal to 1. Meaning I'm not gonna just change the state created by this guy. That's all I'm saying. Which means that this guy can always be phased or parameterized in some phase. So if I take this, then my field operator will look like it's the theta alpha p to the minus I theta of the dagger, and then I shall, of course. But here, good thing is that alpha is a Hermitian conjugate of alpha dagger or vice versa. So I can always just absorb, just redefine what I call alpha and then what I call alpha dagger. Because it appears to be the exact same phase. So if it were not this hermiticity property, I would not be able to do that. Okay? Therefore, if I do that eventually, my field operator will just be that. So this satisfies all 5 properties of being causal, real, scalar. Okay, now I have shown by explicit computation that technically can be done, but this does not. This exercise is great, but this exercise does not show one very important aspect of it. So let me say in word what just happened, and then I'm gonna actually demonstrate. When you try to synthesize quantum mechanics with relativity, in particular, if I accept the form of the field, then and this is satisfied Lorentz transformation property, meaning I have to put FG there. Now, causality in quantum mechanical theory can be incorporated in a consistent manner only if for any particle, meaning for any simple harmonic oscillator, for any particle, you have to introduce what is known as antiparticle in such a way that there's a causality violation looking effect that it should be exactly canceled every time that happens. This is what is demanded. So first of all, introduction of an antiparticle, which you will see by eye from now, is demanded by unitarity or quantum mechanical property of the field. And then causality demands that they should be correlated in such a way that there are causality violation seemingly, or it should be canceled out every single physical process. That's why you see there's a quantum mechanical causality can be there. Okay? So in order to see that, this particular example actually misses out that point. So therefore, I'm going to go into that route and explain. Okay? So again, the statement is a synthesis of quantum mechanics with a special relativity, particular causality, can be achieved only if for every particle with mass and charge, say, electron has a charge -1, there must exist, meaning the formulation demands that you have to introduce another particle, any particle, who has the same mass but opposite charge. And that they have to link together, right? So that is the crux of the discussion. So I'm gonna go through that exercise. This is almost there, but I just missed it out.
Professor,
Yes.
is it okay if I interpret that by X as something like antiparticle and particle at the same time?
Yes, good. So that will be eventually interpretation. So if you interpret this as a particle part of it, this is any particle part of it. But it happens to be that in this permission operator or real scalar field, any particle is the same as particle. So you don't see this type. So this equation, therefore, is the cancellation of the contribution from the particle with antiparticle, and that demands that the mass of the antiparticle must equal to antiparticle. Otherwise, the cancellation will not work exactly. But you'll see that by eye, which is also instructive exercise anyway. So that's good. Question. Yes.
So if X and Y are timeline separated, what should be the value of the delta Phi?
Good. So then first of all, you cannot split this. So you have two genuine contributions to that. Each of them are not zero. Don't cancel. So you should get non-zero answer as you would expect, because you want to produce something at one point in the sentence somewhere. So you should get some non-zero probability test. Probability M. Okay. Any other question? Yes.
저 기계의 항이 별 0이 아니잖아요.
Yes.
그걸로 인해서 파생되는
So, okay, the question is, since this is, I will demonstrate immediately, this is not zero. Even outside of light bulb. I thought the question is, because of that, there's any phenomena that coming from that thing. Well, first of all, because of that, again, Qn plus SR demands that you have to include either particle together with the particle, always. Otherwise, you will not get the causal physics out of it. And two, because of that, if you look at now time-like events, then you get all non-trivial physics coming out of that because it's non-zero. And it depends on the separation, it depends on the parameter of the theory. Okay, so let's actually look at that phenomena. So that I'm going to introduce a complex scalar field. So complex scalar field, let me write it as F to the bottom. And then let me pick a two scalar field that I constructed here. So I'm just gonna put one scalar field plus second scalar field with I divided by 2. Everything divided by 2. Okay, so that's a complex scalar field. And obviously this is not equal to its own conjugate. If you conjugate it, writing this visual part. 2, because they are Bernoulli. Obviously, this is not equal to cell, so it's complex, it's different. So let me write how this thing looks like. So now I'm just gonna combine the two real field operator that I constructed here. So that will look like alpha 1 plus alpha 2 I into the over 2 into minus I p dot x. Well, let me write and then say something. Into the line index. If you naively it's matching by. There is a third point here. But I'm going to be a little bit sloppy, but you can sort it out. So when you have a phi 1 and phi 2, suppose at this moment I don't know whether what is the mass of the particle this guy creates versus the mass of the particle that guy creates, right? I just combine random way here or in this language, right? So in principle, like the phase appearing plus minus p dot x here, even though it may be written as p versus the phase I'm writing here, they will not in general be exactly the same, right? Because this guy has, for instance, momentum, even if the same momenta, it can have a different mass versus another mass. So when I combine this thing, obviously that requires that the phase appearing in phi 1 field versus phi 2 field must be exactly the same, right? Otherwise I cannot combine it this way. Okay? So good. But then here is the logic of the exercise I'm gonna proceed. But the moment, let me just assume that they have the same phase. Meaning the moment when I say that I'm sort of identifying the mass basically the same. Then I'm gonna show that the causality anyway demands by self-consistent check that the mass also needs to be same anyway. Okay? So there's a little bit of, in other words, I'm not doing mathematical derivation here. In order to do the mathematical derivation, I have to write everything separately, assuming there's different mass, and then I should go on to the checking of causality, and I have to show that it should be exactly the same, right? So which you can do that. It's not that much difficult that I'm demonstrating, but for the sake of time, let me just being sloppy a little bit, just write this way first. Okay, which is again done only if measures are the same, but as a self-consistent check of my exercise, I will show the causality in the end eventually also demands the metric the same too. So it is consistent check. Now let me call this to be my alpha p. Now this is not dagger of alpha. You see that? Conjugation of that thing is alpha 1 dagger minus I times alpha 2 dagger. Oh, sorry, I missed something. That why your face is like, what's going on? Dagger. Sorry. Good? Happier or happy? Or never happy? So this is not same as this alpha dagger, right? Because if you take dagger, there's minus sign, but there's a plus sign. So I'm gonna give another name, beta helium dagger. Right? Good. I wanted to say something about the field. Let me do that. Yes, let me do that. Remember, I said I wanted to say something about the field. And if I don't say anything, just remind me. Okay? That's the important summary. So here, therefore, beta of P is alpha 1 minus alpha 2 over 1, which is linearly independent from alpha. Good. Now, start given this alpha I equal to 0. Again, I'm slightly dropping the momentum part here. Alpha I dagger alpha I dagger to 0, and then there's alpha j dagger is equal to 2 pi q, the usual commutative relations. You can show that alpha and beta also satisfy the same commutative relations. Okay, so this shows that as an alpha, let me just write the key equation only. Q dagger Gauge form, I mean the consistent harmonic oscillator. Okay, so it's just taking a different basis. Either you just look in terms of alpha 1 or alpha 2, or you just look at the alpha beta basis. Okay, anyway, you had 2 degrees of freedom, right? There's a 1 degree of freedom, 2 degrees of freedom. You combine it together. So anyway, you should keep 2 degrees of freedom somewhere. And this is how you see the alpha beta separate. Anyway, so that good. Now let's check the causality of this situation. So now causality equation. We have to say that the phi of x, phi of y should be 0. Phi of x by dagger of x by dagger of y should also be 0. Finally, phi of x by dagger of y should be 0 outside of y. Right? So everything should vanish outside of y. Okay? Now, these two are trivial once you understand this part. Because this guy has alpha. Oh, but in addition to this, I would you should get the alpha beta either with your deck or not. Everything is there. Meaning alpha beta are independent. They don't talk to each other. Okay? So here there's alpha, the only thing that you have to look at is alpha part. But this guy also has only alpha, but not alpha dagger. Right? And alpha commutes outside of LIGO. Here too, there's a alpha dagger beta. So beta cancels, meaning beta is 0, alpha dagger is 0. Right? There's no non-trivial thing in these two things. So let's check the third. Okay? If you missed it, check it. This is alpha plus beta dagger, alpha plus beta dagger. Look at it, whether there's any non-trivial commutation relations you can get. I'm saying it's 0. So let's look at the last one. Because that captures it. I'm going to demonstrate. Okay. Was there? Yes.
세 번째 거 체크하려면은 맨 위에 있는 두 번째 라인에 프로젝터들 하나 더 넣어야 되죠. IJ 거리.
Yeah. Yes, that's right. So there are 2 separate permission, simple harmonic oscillator, right? And then I just choose different bases. I'm saying alpha beta base ordered by 2 separate simple harmonic oscillator systems. So because of that, these 2 are automatically 0. Okay, and then let's check the last one. Any other question? Yes.
In this example, phi is not permissional.
Very good.
So why
am I doing?
Yeah.
Good. So this is an important question. And so let me rephrase the question. The reason why we start talking about the causality is because observation shouldn't affect outside of Lightbound. So we have to check all the Hermitian operators of the theory should commit outside of Lightbound. This is not Hermitian, so what happened? The logic, I believe, is that in quantum field theory, eventually you will see a lot of non-Hermitian operator like this. Then you're going to construct a lot of Hermitian observable operators, and you're going to check causality. But the minimal, or maybe even mathematically, the only way to ensure that all Hermitian operator you construct out of a non-Hermitian field operator being causal is to demand that even this field operator as a building block of the rest of the observable are just 0 outside of line. Okay, otherwise, now you have to, there's an enormous amount of constraint on what are the possible observable operators you can construct out of it. Now, I don't know whether this is the mathematical theorem level, but that at least I can see that so logically, if you have a set of non-Hermitian but fundamental field operator, meaning field operator as a fundamental description of physics, then if vanishes outside of Lightbound, then by construction, every observable you construct out of that will also satisfy causality. But if you don't demand it at this level, then you have to worry about line by line every single observable you have to. And probably at some point you can have enough to set up a Hermitian operator constructed out of a non-Hermitian operator. And if you demand causality, probably you can show that this also must anyway is outside of line. But I'm not saying I haven't done that exercise, but I know this for sure. That's a great question. Any other questions? All right, so let's check this, and this is important and very informative exercise. Okay, so I told you already this super abstract statement, super deep, fancy, abstract statement, right? You have to introduce and the particle, you have to cancel, blah, blah. I told you that. But this exercise, you will see line by line where they come from. Okay, so follow me. Let's look at this. Okay. So here, I can decompose this guy. Let's see if this makes sense to you. Alpha, holy shit, plus beta minus, oh my god. Is this as bad as Weinberg notation or close? Similar. Okay, but it's complete notation. Let me explain what I mean by this. Oh, who did that? Who did? I saw somebody in here. But anyway, so this. Let me see if I can get this right. Beta plus y beta y.
Why are both beta?
Yeah.
What? So
Yeah, what does that mean? So let's look at this operator. So this guy has alpha part, which is positive frequency part, right? According to historically misleading nomenclature, but nevertheless we're going to use it. Remember that. You're not remembering that. I explained to you. Okay, there's an alpha part, there's a beta part. Alpha part is like positive frequency part, right? Positive frequency part, and beta dagger is this negative part, right? So phi can be written as positive frequency controlled by alpha operator, and then negative frequency controlled by beta dagger. And if you take the permutation conjugate, you will solve this too. So permutation conjugate should come with beta positive. Oh, was that your question? Yes. I'm sorry. Anyway, I had to explain. There's a negative part with controlled by alpha. Is that clear now? Good. Let's look it up. So good. Plus x. Let's see if I can do this. Alpha minus. So that we decided to call delta plus x minus 1. Remember that? Okay. And then I also said this is controlled by the mass of alpha particle, right? This is all about alpha stuff. Okay. All right. Now, what else? This should be 0. I don't have to worry about it because alpha beta all completely commute outside. Oh, just commute. They don't talk to each other. There are two independent systems. So then there's another one. Phi beta minus x. Phi. And so this is the minus of that thing. That is minus of delta plus x minus y controlled by beta s. Okay. Now, what does that basically mean? So I have not explained to you the basic meaning of this particular object, right? Yet, right? But before that, you can already see that. Oh, how do I demand that this is 0 outside of 1? And at least you now immediately see that suppose alpha system create all kind of particle, beta system create another kind of particle. Suppose modulo this blue fine print that I mentioned to you, right? I was slightly that much. Then looks like there's a one propagation of an alpha particle. There's another guy contribution to the causality equation from beta particle. If they are nothing to each other, whatever, then you will never get to the right answer. Good? So causality, demand, in this case, that even if you say, oh no, this guy should create one mass particle, this guy should create another mass particle, but by the time you demand that I'm gonna combine together a single field operator, and then I'm gonna use this as a middle building block, you are not free man. I'm sorry. So you have to demand that, therefore, alpha particle mass must equal to beta particle protocol. No option for you. I'm sorry, but that's your life. But I have to say one more thing about it, which is this is a complex field, right? This is a complex field, and we are going to spend some time talking about symmetry. But complex fields, in the theory, enjoys a sort of symmetry, and it has, for instance, if this guy transforms under +1 alpha this, let's understand what this, okay, if you don't understand what I'm talking about here, let me think which way might be better. Should I just assert? Would that be assertive enough? You just swap? No. Okay, so I have to explain. So what I mean by it is this. So there are two particles here, alpha particle, beta particle. Eventually what I'm gonna say is that if alpha particle carries charge 1, beta particle should carry charge -1. They have to have opposite charge. How do I see that? One formal way of seeing it, which you will spend time to learn about eventually, is that if you transform by operator under some U1 phase transformation with some Q. So this is a transformation parameter, and this is like, if you like, this is a charge of the particle. Okay? But then from this equation, you immediately see that by Dagger operator, if just complex conjugate this should be I of -Q alpha by Dagger. Right? This is what you can see. Even though you don't know why you have to do this transformation, at least you see that if I say this is a good thing to do, whatever that means, this also follows from that. At least you see that much. Good? So now let me interpret. Under this arrow thing called symmetry transformation, alpha picks up +Q. But beta dagger picks up +Q. Because it's alpha and beta dagger. So from here, if alpha picks up +Q, alpha, oh my god. Data, oh, okay, I already removed the data part of the story. Thanks. So theta, alpha, then either you use from here or source from here. So here you have instead of beta plus alpha dagger. Right, so beta instead goes with -Q theta. So what this shows is that if alpha system create a particle, if it carries charge Q, the beta system create a particle who has charge -Q. All right. So now let's combine all this together before we put a little bit of more physics context. Now let's start with the causality equation. Okay, I'm just gonna smash. So this is quantum mechanics context of causality because I'm checking this in terms of operators. And that is true, again, if there's a sign cancellation 100%. Therefore, exact same mass, but opposite charge. So whenever you want to introduce a particle, say, I want to have a quantum mechanical description of relativistic particle A. So here's my alpha dagger system, charge, whatever, blah, blah, mass something. I'm done. No, you're not done. You are forced. It is demanded that you have to introduce another particle, same mass, opposite charge. There is no option, right? Otherwise, causality will never be there. So this is how tight the game is between the quantum mechanics and special relativity. You ought to introduce new particles than you thought you're doing. Now, going back to the earlier discussion, you see, for real particles, it happens to be that alpha, what I call alpha and beta bits were the same. So their particle, antiparticle were just the same. That's why I said it's a missing or obscuring at least one important property. That's why I introduced complexity. Okay. Now, I'm gonna have to say two things. 6 minutes is good, but questions. Hopefully you appreciate what I'm doing. Yes.
Do you mean that any possible charge should be reversed in the antiparticle?
That's right. Yes.
Do you mean it is because of?
Where the sound comes? Yes, sorry, yes.
Do you mean that is caused by causality?
Sorry, causality? Yes.
Is that discussion related?
This is, yeah. So when would this be true? There should be, so one of the two things that I'm gonna say now is that what is the physics meaning of that thing? Okay, this object. And I have shown you that, yeah, this is zero, non-zero, oh. But this is related to the fact that you're creating a particle and then propagate and check whether you see the guy or not. But then, if you have the physics interpretation, this is the propagation of particle with the mass and charge carrying it. Okay, which I will show immediately after. So the reason why I talked about this guy is that whatever this field operator does on you, which I will tell you that this creates a particle, beta particle, who has momentum p, momentum mass m beta, and charge minus q. But what this guy does for you is you create an alpha particle, momentum p, mass m alpha, charge plus q. They have to come with the set. The causality in quantum mechanical sense demands that they have to come together all the time. But, oh, is that true? That sounds like exactly crazy thing. Electron, tell me, muon, tell me, anti-muon. Whatever, give me any particle name, I just put anti immediately, done. That's true. Everything we have since all. Okay? What about Higgs? Oh, Higgs is its own antiparticle. So that's how we go out of that law. Photon, it's all antiparticle itself. Okay, yes.
I think the one you said, what you have said before, the antiparticle only exists in complex scalar field.
No. Well, I think it's semantics, but continue.
So can we just do the same thing? Can you think of the antiparticles of just a real scalar field?
Which I did first. There it happened to be that alpha is identified with the beta. So antiparticle is the same as particle itself. It's called the neutral particle that doesn't carry any charges. Okay. Do you appreciate this old concept coming into play together? Okay. So so let's look at, before I make some physics. Hold on, I thought the clock was 08, but not 12. So we ended up on time. Let's do it. So the field operator, let's write it out. So now you have seen this, but I'm just gonna take this expression and then summarize our discussion so far. Meaning, hopefully, you see not just that equation, but you see 5 different information hiding inside of this single expression. That's why I wanted to be able to do it. So first of all, yeah, we consider minimal combination. That was one of the things we talked about. Yes. And yeah, I know that in principle there can be the parameter, but there should be just a function, not function, but just what constant because of the Lorentz invariance. So that part was because of the Lorentz invariance. Yeah, this particular and only this form was dictated by the translation. Okay, we saw that. Okay. Now, causality demands that these cannot be, first of all, any random thing. First of all, they should be correlated in such a way that for each alpha with the mass m and the charge q, I should have this guy, say mass minus charge. Okay, so this equation has all that information. Later, I will reformulate the quantum field theory. Okay. But there now, this will pop out of as if it's just solving one single differential equation and providing coefficient to the operator. In that discussion, you will completely miss all this content, severe content of a fight between quantum mechanics and special relativity. Okay, so hopefully now you can see that all information hiding. Okay, now I'm not giving up. So let me spend a couple more minutes and just explain the meaning of that really. Okay? So let me just take like 3 minutes or something. I think I came 3 minutes later after, right? Anyway. Yeah. Okay. So I'm not due. Who has, by the way, just for the future, who has a class right after this class? You in this building, or you have to run somewhere else?
Just
Next, okay, good. Anyone else? Okay, you'll start there. Okay, good. Let's move on. So first of all, non-zeroness of delta. Let me quickly show that. So let me drop the answer for a second. And I told you that this is equal to, if you actually compute it, let's see. And then let me remind you that we did exercise once we prepare particle, and then we did the time evolution with the relativistic Hamiltonian, random scooped up Hamiltonian, and then you check whether you see the guy somewhere. When we first encountered causality violation, the expression was yes. And this was the expression even as a Lorentz-Invariant formulation of the thing. Okay, meaning there's a you can make the Lorentz-Invariant measurable. Anyway, you do it, you arrive at this. You can compute this thing. Okay, so that was again particle prepared at time equal to 0, which was localized, and then do the propagation as this Hamiltonian, and you measure it. And we saw that this is non-zero outside the line. That was some exercise we have shown, like branch curve, blah, blah. Now, if you compare these two, you see that delta, this thing, x minus y, or just limit is look at x, just drop the y. And then if you do time derivative of this side, then you're pulling out time derivative, forget the y. You're pulling out minus I times energy. The energy cancels, right? Therefore, there's a 2, there's minus I, that is equal to minus I over 2. And then once you have that, the rest of the expression looks exactly the same as this. Okay, so that is equal to x e to the minus I Hamiltonian side, which we learned that this is not equal to outside the line. Okay. Now, here's a simple logic. If this thing is not 0 outside the line font, sorry, if this is 0 outside the line font, you know that whose derivative is also 0 outside the line font. This is simple to see because you start take the 0 function and doesn't matter what you do after that, right? Therefore, contraposition is true. Negation of that thing implies negation of that thing. Right? So therefore, if this is non-zero, this is not 0. Therefore, this function is non-zero outside the line. Okay? So this is a technical point, but we assume that throughout the discussion about causality. Okay, that's one point. And just 2 more minutes, I promise. Just to appreciate the meaning of this thing, you can compute the following. So in this case, in this example, the one particle Hilbert space consists of one particle Hilbert space of that guy with one particle Hilbert space of that guy, right? So one particle Hilbert space consists of 2 pieces. Then A, momentum P, mass alpha, charge Q guy. And then momentum P, beta, minus charge Q guy, and Q guy. Obviously, we know that the mass should be the same, but I'm just writing more careful way, even if it looks like redundant, right? So now what you can do is that take this operator, acting on the vacuum, and then check what is overlap with that guy with this alpha particle sector versus what is overlap of that guy with the beta particle. You can ask that question. This will give you a sense of physics, right? Because I want to know what this does to you. Right? So first I told you therefore that the one particle sector of this box space, remember, is vacuum, one particle sector, two particle sector, and many particle sectors. And I'm saying, what does this do, basically? If you take the guy active in the vacuum, it will create a single particle. Which one? Well, that's clear because this guy is create annihilation operator, so alpha part will just kill it. It's zero, right? If you take alpha acting on the vacuum, that's zero. So this guy, this state has zero overlap with alpha particle sector. On the other hand, that again state has a beta plus, which is creating this. So this will be non-zero, and this you get this if you actually do the computation. I mean, trivial to that the coefficient of that thing in this thing. And likewise, if you flip it, now if you instead of take this guy, now you get this part being zero, you get e to the IPX. So phi dagger has an ability to create alpha but kill beta or vice versa. Right? It creates one guy, but it kills the anti guy, vice versa. But it comes with this e to the IPX all the time. Either particle, antiparticle. Again, both of them comes with either IPX. None of them has either a minus IPX guy. You might say, oh, therefore, what is the interpretation of this? Is this a positive energy state or negative energy state? Right? Remember, I introduced like positive frequency mode, negative frequency mode. Historically, people say negative frequency mode signals antiparticle. But I'm showing you both comes with this. And I leave you as an exercise to check whether this actually corresponds to positive frequency or negative frequency. Come back to me next time. Okay? And then we will just talk about this for like 3 minutes at the beginning and then move on. Okay, with that, we're wrapping up this part of the discussion, and next time we will start moving on to scalar relativity. Questions?
오케이.
예.
오늘 내용 교재 어디에 나와 있나요? 나와 있는
여기요?
아, 그렇군요.
네.
원래 마지막에 필드 관련해서
네, 그게 아까 뭐 정리해. 이 필드에서 5가지 딱 적어서 어떤 피처가 그거에 해당하는지 스스로 매핑할 수 있는지 체킹하면 되겠지. 그러면은 똑같은 이퀘션 두고 어떤 사람은 저런 게 있었구나 할 수도 있고 어떤 사람은 5가지 얘기할 수 있겠죠. Relative variance, causality,